In this presentation, I will be talking about model reference adaptive control for prescribed performance and longitudinal control of a tail-sitter UAV. Control of tail-sitter UAVs is a complex task, and in the recent literature, several different control techniques have been used to solve the problem. Specifically, classical MRAC has been applied to a tail-sitter UAV's pitch dynamics exclusively. And unfortunately, classical MRAC cannot impose user-defined constraints or rate of convergence on the trajectory tracking error, which we would like to address so we can achieve user-defined levels of performance. So we designed a novel control architecture in an MRAC law to control the tail-sitter UAV's longitudinal dynamics, despite uncertainties in aerodynamic coefficients, lack of control surfaces, nonlinear dynamics, and other actuation, while satisfying user-defined constraints on the trajectory tracking error and imposing an arbitrary rate of convergence on the tracking error. Into some modeling and assumptions, we have the three reference frames listed on the left, and that allows us to define the pitch angle, theta, the angle of attack, alpha, the flight path angle, gamma, the position of the vehicle, T upper and T lower, which are the thrust forces produced by the upper and lower sets of propellers, and L, the moment arm. And as a result, we have the translational dynamic equations, where Fx is the x component of the thrust, we have the x component of the lift and drag, Fz is the z component of the thrust, mg is the weight, and we have the z component of lift and drag as well. So Fx and Fz are defined as shown. T upper and T lower, though, must be non-negative, since commercial off-the-shelf propellers and motor combinations typically can only apply thrust forces in one direction. Furthermore, the lift and drag are modeled as shown here. However, any formulation whose functional form is known and coefficients are unknown can be used in the MRAC framework. Here we have the rotational dynamic equation, where my is the moment of the thrust force, ma is the moment due to aerodynamic forces, and both are defined as shown here. So the plant's dynamics can be cast in this form, where the matrix G is not full rank, and hence the system is underactuated, which means that the position and pitch angle cannot be controlled independently. So let's move on from the modeling portion and talk about the drawbacks of classical MRAC, the first of which being that it offers no mechanism to satisfy user-defined constraints on the trajectory tracking error, as evident in this adaptive law. Furthermore, if we define the rate of convergence of the reference model, alpha max, it's actually been proven that the dynamics of the error and of the reference model are characterized by the same rate of convergence, alpha max. Therefore, the plant state reaches the reference model state as soon as or after the transient dynamics of the reference model has decayed. We want to design an MRAC law so that the user can select a parameter alpha such that the rate of convergence of the trajectory tracking error is faster than the rate of convergence of the reference model. Model reference adaptive control for prescribed performance meets this requirement, verifies constraints, allows us to set arbitrarily large adaptive rates, doesn't involve estimators or differentiators, and the user can retain the same reference model. So in this framework, the user can define the constraint set E and the constraint function H sub E, which satisfies these properties. We can consider the feedback control law, denoted by phi, and define the reference model for the error's transient dynamics. So now we can define a few quantities, most importantly, epsilon, which captures the difference between the trajectory tracking error and the reference model of the transient aerodynamics. The last equation is actually a matching condition for the reference model of the error's transient dynamics and is an additional condition on the user's choice of a transient, which has to be a Hurwitz matrix. Now we can define the adaptive laws as such, and notice the constraint function in the denominator in both of the adaptive laws. And that leads us to our first theorem. If the trajectory tracking error starts within the constraint set and the constraint function satisfies this property, the matching conditions are verified, and the real part of the largest eigenvalue of a transient is less than the real part of the smallest eigenvalue of a ref holds, then the error and the adaptive gains are uniformly bounded, the error stays within the constraint set for all time, the error converges to the origin, and the rate of convergence is imposed. Now we want to modify the MRAC law for output tracking so that the measured output y tracks the bounded reference signal y command. So we have the measured output y, and we define the integral of the output tracking error and the augmented state vector. So now the integral of the output tracking error is part of our system state, and we have the augmented plant dynamics. Now consider the feedback control law, which is comprised of an LQR baseline controller and an adaptive controller, as well as the adaptive laws. And that leads us to one of our main results. So if these conditions are verified, which are similar to that of the last theorem, then the error and adaptive gains are uniformly bounded, the error stays within the constraint set for all time, the error converges to the origin, the rate of convergence is imposed, and the norm of the output tracking error is uniformly bounded. Our control strategy for the quad-order biplane is to first define a reference trajectory, apply MRAC to compute forces needed to follow that reference trajectory, and then use those virtual forces to determine the orientation of the desired thrust force denoted by theta command. And then lastly, apply MRAC to compute the moment of the thrust force needed to follow theta command. Now we have an outer loop and inner loop structure. In the outer loop, if Fx and Fz are set as such, then the outer loop dynamics are in MRAC form, and we can apply either of the theorems presented earlier. Now we can define the desired orientation of the thrust vector, theta command, in this way. This choice of theta command ensures that it is always in the interval 0 to pi, which physically means that the thrust vector does not point towards the ground. And it also helps in avoiding switches between extremes associated with oscillations of Fx and Fz around 0. Here we have the inner loop model, and similarly, it is also in the MRAC form. Now we can set the desired thrust force that realizes Fx, Fz, and My. And for example, it can be determined as a solution of this optimization problem, in which we want to minimize the thrust force subject to these constraints. However, this problem may not have a solution because the pitch angle theta is fixed and the total thrust T is positive, so we may not be able to satisfy these constraints for arbitrary Fx and Fz. And furthermore, the resulting control policy may be overly aggressive. So we propose the approximation of the total thrust force as shown here, where theta max is user defined. In the first case, we project the desired force onto the body reference frame. In the second case, we use gravity to descend quickly whenever Fc is negative. And in the third case, which captures when the orientation of the vehicle is not close enough to the desired orientation, where close enough is captured by theta max, we set t hat to a default value. Now we allocate the thrust force to the upper and lower sets of propellers according to these 5 rules, which ensure that the moment of the thrust force is always realized. Now we integrate the inner and outer loops by stacking their states into one vector and defining these matrices as such. And this approach avoids problems with the 2 nonlinear system stability. And we can apply classical MRAC or theorem 3.1 by setting the reference model parameters as such. Kp and Kd are user defined, and define the reference signal in this way. This approach requires an estimate of the first and second derivatives of theta command. Alternatively, you can apply theorem 3.2, which does not require an estimate of the first and second derivatives of theta command. In this section, we compare the classical MRAC controller in theorem 3.1 in a simulated VTOL mission, where the user-defined trajectory is given as shown here. This is a table of parameters used in our simulation. The third column are the actual aerodynamic coefficients, and the fourth column are the estimated aerodynamic coefficients. On this slide, we showed the x and z position versus time in the top and bottom plots respectively. Clearly, the model reference adaptive control with prescribed performance outperforms classical MRAC in terms of tracking the user-defined trajectory. Here we show the pitch angle versus time for prescribed performance MRAC and classical MRAC. Here we show the weighted error in the outer loop versus time, and in the bottom we show the weighted error in the inner loop versus time. Clearly, classical MRAC violates the constraint represented by the pink line in both cases, whereas the constrained version does not. Here we show the control versus time for MRAC for prescribed performance in the top and classical MRAC in the bottom. We have also evaluated the performance of the proposed control architecture in theorem 3.2, but due to time constraints I cannot dive into the plots, so I encourage you to check the paper. Here we acknowledge our funding sources. Thank you for watching.